All right. So let's do a little bit of review, but not too much because I want to show you the p-value approach to hypothesis testing, which is kind of the more formal approach. But let's do a little bit of review. So we talked about the steps for hypothesis testing. Which step one was to state our null and alternative hypotheses. So state the hypotheses. In general, that's going to look like this, right? H naught is that P is equal to P naught, where P naught is the value you want to compare your sample proportion to. And the alternative hypothesis is that P is not equal to P naught. This not equal to, what we're going to find today is that that's the default. So if you're not sure, then use the not equal to. But it's also the only one that we can test for using a confidence interval. So this is all we can test using a confidence interval, and not equal to is the default inequality. We will be able to test things like less than some value or greater than some value. But in general, just remember, maybe yellow highlighter, that's the default. And let's also remember that P naught is the null value, which is the value we want to, this doesn't look like the null value, which is the value we want to compare our sample proportion to compare our sample to. Because later we're going to talk about not just the proportion, but also the mean. So in general, the null value is that value that we want to compare our sample to. And then in step two, we were going to do the test. And that's where we, for the confidence interval approach, we calculate the confidence interval. Calculate the confidence interval. For the p-value approach, we're going to calculate a test statistic. So that's what I want to introduce today, is what is it and how do we use it? Calculate the test statistic. I'm being intentionally vague because calculating the test statistic applies to every type of question that we're going to encounter. So it's not just for one sample proportions. It can be for one sample mean, two sample means, many samples. So it applies across the board. Step three, I was calling it gather evidence, I guess. Which for the confidence interval approach, we drew kind of a number line where we have our interval. So we marked out our interval, and then we had our hypothesized proportion was either outside the interval, right? And that's what gave us enough evidence to reject H naught and say, okay, well, my interval is over here, right? But my hypothesized value is outside that interval. So I'm let's say 95% confident that it doesn't contain the null value, right? Or we might have something that looks like this, right? Where we might have our confidence interval. Oh, not sure what happened there. We'll zoom in. And our P naught was somewhere in the interval. Okay. this first one, you have enough evidence to reject H naught, right? And here, because the null value is inside the confidence interval, then there's no reason to say that the null value is not does not apply, right? So in this case, we do not have enough evidence to reject H naught. Those are only two options, right? We either have enough evidence to reject H naught or we don't have enough evidence to reject H naught. There are no other options for us. Okay. And that's because we do all our testing assuming the null hypothesis is true. Now, for the p-value, I'm just going to reiterate the definition of the p-value. The p-value is the probability of seeing something as extreme or more extreme than what we saw. And I'm going to fill in and show you what that means in terms of our calculations. But for now, let's just reiterate the definition of the p-value, which is the probability of seeing something as extreme or more extreme as what we saw in our sample. And the most important part is that that's assuming the null hypothesis is true. Assuming the null hypothesis is true. So if we approach it from this angle where we have the definition, then, okay, if the probability of seeing something, something as extreme or more extreme as what we saw in our sample, well, assuming the null hypothesis is true, if the probability is really, really small, then that gives you enough evidence to reject H naught, right? If the probability isn't that small, then you don't have enough evidence to reject H naught. So what we're going to do is we're going to introduce a threshold to determine what's small enough. And spoiler alert, it's 0.05. Okay, and so we'll develop that a little bit more. I'm going to bump this down. I stole some clips from the textbook that I wanted to introduce, so not clips, screenshots, I guess. For the conclusion, goes back to step 3, right? So they're all daisy chained throughout here. And once you kind of get the hang of it, then you can do any hypothesis test for any type of question, right? And so that's what's kind of fun about it, but it is a lot to wrap your head around. So your conclusion is in 3 parts, right? So the first part is compare the null value to the confidence interval, right? Is it inside the interval or outside the interval? Or we're going to compare the p-value to the alpha level. That doesn't mean anything right now, but that's okay. It's good to have seen it. Compare the p-value to the alpha level. I'll write it out. Although usually I just do the little alpha. Where can I give myself one more line? I can bump this all up one. Okay. The second thing that we're going to do, and this is the same for the confidence interval approach or the p-value approach. And so now we state our conclusion in terms of H naught, right? But in both cases, we're going to assume the null hypothesis is true. So your conclusion in terms of H naught. And then finally, the reason you're going through all this work is your conclusion in terms of the question. And I know it sounds crazy, but that's the part that people forget about mostly. Conclusion in terms of the question. And that's, we'll call that the end of our review, because it's the end of the page. Okay, so when we are doing hypothesis tests, we're going to come to a conclusion, right? We're going to have enough evidence to reject H0, or we don't have enough evidence to reject H0. But we can be wrong, and we can be wrong in two ways, right? If we reject the null hypothesis, there's a chance that we shouldn't have, right? Or if we don't reject the null hypothesis, there's a chance that we should have, right? And so we need to talk about these decision errors, as they're called. So decision errors. When conducting a hypothesis test, regardless of the p-value or the confidence interval approach, CI or p-value approach, just in general, right? There's always a chance that our conclusion is wrong, right, is an error. There is always a chance our conclusion is wrong, right? And I'm going to bump this example down because that's the one I want to use later. Oh. There. But the easiest way that I find to summarize these decision errors is with a table. So this is from the textbook. And so what you're going to have is you're going to have some conclusion that you've come to, right? You either don't have enough evidence to reject H0, or you do have enough evidence to reject H0, right? And so there's some truth, but the key is to remember that we don't actually know. We will never know the truth, right? That's why we're hypothesizing about it. Sorry. So if the truth is that H0 is true, then if H0 is true and I decide I'm not going to reject H0, then that's fine. That's the correct conclusion, right? That's not an error. But if I reject H0 when H0 actually shouldn't be rejected, right? That's what we call a type 1 error. Okay. And so the other way we could be wrong is if the alternative hypothesis is true. So that means that we should be rejecting H0. And I decide not to reject H0, that's what we call a type 2 error, right? If the null hypothesis is wrong and we should be rejecting it and I reject it, then that's fine, right? And so a type 1 error is rejecting the null hypothesis when H0 is actually true. And a type 2 error is failing to reject the null hypothesis when the alternative is actually true. So a little bit tricky, but you have to just kind of I find that this table is really helpful if I just jot it down to help me remember. But the main one that we're going to be concerned with is the type 1 error. Okay, so that's when I've rejected H0 when I shouldn't have. Okay, so we're trying to minimize the type 1 error rate. Okay. In hypothesis testing, we are usually trying to minimize the type 1 error rate. The type 1 error rate. Okay. Whereas if I don't have enough evidence to reject H naught when I should have, usually that's just a matter of my sample size wasn't large enough. I didn't have enough evidence to reject H naught, even though I should have, right? So there's really nothing that we can do there if we have a small sample and it doesn't give us enough evidence, then we end up with a type 2 error, right? But so the one that we can control is the type 1 error rate. How often am I going to reject H naught when I shouldn't have? Right? The type 2 error is usually the result of small sample sizes, right? Or is usually due to small sample sizes, which presumably we can't do anything about. So we can't control the type 2 error rate as easily. So the type 2 error is usually due to small sample sizes, which we can't really control. Unless you have the money and the means to collect a larger sample and you just decided not to, but that would be weird. You are always going to collect as large a sample as you can, right? And so it's not really an issue. Okay, but the type 2 error is kind of out of our control, and we're going to focus on the type 1 error rate. Okay, so let's see here. The p-value approach to hypothesis testing is the more formal hypothesis testing method, and it's also the one that you would use in publications. And if you're going to read, research papers and stuff like that, then they're going to be using the p-value approach. And I'll show you the connection between the confidence interval, but we talked about the shortcomings of using just the confidence interval approach. Things like, well, we can only test if p is not equal to some p naught, right? So if there's been a change, whereas some applications we might be interested in, has it decreased significantly or has it increased significantly? And also it doesn't tell us how big of a change we've seen, right, from the null hypothesis. And so the p-value is going to give us that. So the p-value approach to hypothesis testing is the more formal approach, which is used in publications and academia in general. So it depends on, I know you guys are in biology, but the other group that takes this course is in data science. And so they would be more interested in confidence intervals to try to figure out what the value is. But in biology, of course, we're interested in publications and just kind of real proof. So then we're going to focus more on the p-value approach. Okay, so we already decided what the p-value is. Now, that didn't really help us much, right? But let's see here. What I want to do is go through those steps for hypothesis testing again, but only focusing on the p-value approach. Okay. So here are the steps when using the p-value approach. Okay. I'm going to call it step 0, which is to check our conditions, right? We already talked about the conditions for doing a confidence interval. So we had to make sure that we had independence. So our sample is randomly selected. We had that optional condition of our sample size has to be less than 10% of the population. And then we had the success failure condition, right? I have to have at least 10 observed successes and at least 10 observed failures in order to do a confidence interval or build a confidence interval. That's still true, but it's going to change just slightly for the p-value approach. Okay, so step 0 is to check the conditions. Okay, remember when I introduced the conditions and I said, okay, well, let's see here. P hat follows a normal distribution centered on P with a standard error of P times 1 minus P or Q over N. Now, we said, well, I don't have P. I'm trying to learn about what P is. Oh, I set the Google off. I don't know why. It was the square root. No. So we said earlier, okay, well, I don't have P, right? And so we would use P hat instead, right? So earlier, right, for the confidence interval, we used P hat as an estimate for P, right? So as an estimate for P. Right, so we said, okay, well, it's going to be centered on P hat, so a mean of P hat, and it's going to have a standard error of the square root of P hat times 1 minus P hat over N. Now, we're ready for that follow-up, that extra little blurb that I added, and I said, unless we have some hypothesized value for P, okay? And so now, when I'm using the p-value approach, I'm going to use that hypothesized value for P. So here, we said, unless we have a hypothesized value for P, okay. This is the case if we're using the p-value approach. And that's confusing, right? Because we had a hypothesized value for P for the confidence interval, but in order for it to work out and how we build our confidence interval, we just use P hat. Okay, so now we use this in the p-value approach. Okay. So instead of P hat as an estimate, what are we going to use? We're going to use the null hypothesis that P is equal to P naught. Okay. So this says that therefore we use P naught in place of P. Okay. So then we have a mean of P naught. And remember, the normal distribution says that we can use z-scores to standardize with a mean of P naught and the square root of P naught times 1 minus P naught over N. Okay, so wherever we were using P hat before, we're actually going to use P naught. Okay. So the conditions to check. The independence condition is always going to be there. We have to check independence. Oops. So glitchy. So the independence condition, we have to assume that our observations are independent of each other, which we can ensure by collecting a random sample, right? So the sample was randomly selected is how we check that. Or we have to assume it, right? So either way, you have to make a statement. Either it says it was randomly selected, or you have to say, I'm assuming it was randomly selected. Either way, those are the assumptions or the conditions. The optional independence is that n is less than 10% of the population. That's optional. You can check it if you want to be really thorough, but you don't have to. The success failure condition says that, okay, before we had to have at least 10 observed successes and at least 10 observed failures. Now we're going to change that, right? Because that was NP hat has to be greater than or equal to 10, and NQ hat had to be greater than or equal to 10. But now instead of using Q hat and P hat, we're going to use P naught and Q naught. Okay, so we're going to check N times P naught. P naught is the hypothesized proportion. So that makes this the expected number of successes and failures, which is the expected number of successes. And it has to be greater than or equal to 10, and N times Q naught, which is the expected number of failures, has to be greater than or equal to 10. All right, so notice that this is the only change here. It's subtle, but it's going to make a difference. Okay. You're still going to have a p hat, so you're going to have a sample proportion that you want to compare to your p naught, but as soon as we shift gears into the p-value approach, then p naught takes the place of p hat in all your conditions and in your calculations for the most part. Okay. So once you've checked your conditions, if you're asked to do a confidence interval and a p-value approach, okay, to the hypothesis test, then you would have to check both conditions, right? So if you want to play it safe, you could just always check both conditions. But if calculating a confidence interval as well as a hypothesis test with the p-value approach, we would need to check both sets of conditions, right? But the independence conditions are the same, and so it's just the success failure condition that changes. We would need to check both versions of the success failure condition. Right. This means you have to read ahead, read through the question to determine what conditions you should be checking. Okay. Need to read the entire, and I'll say therefore need to read the entire question to determine which conditions to check. Huh? I keep sitting on that example for a little bit longer. Okay, so the conditions change ever so slightly, but besides that, Nothing really crazy. Okay. So then step one, we have already seen it's going to come from the question where we state our null and alternative hypotheses. And now let's see here. Step one is to state the hypotheses. And this, it comes from the question, right? So it depends on what the question is. And remember, for a confidence interval, we were only able to detect a change, right? So if you see the word change or kind of different or some other synonym for change, then your null hypothesis is that P is equal to P naught, and your alternative is that P is not equal to P naught. Another option now is that we could detect a decrease or an increase, right? Or, you know, some synonym of that. So a decrease, is it less than some value, or has it decreased from this value, right? So your null hypothesis is always the same. As soon as you've determined that it's a one sample proportion question, this is your null hypothesis, right? So the only difference here is in the alternative hypothesis. And if there's been a decrease from P naught, then P would be less than P naught. Or if there's been an increase, then H naught P is equal to P naught, and HA P is greater than P naught. Now I want to highlight where these link up. Okay. And just notice that the null hypotheses all stay the same. Okay. This, when we're testing both sides, so an increase or a decrease, a change, it doesn't actually care which side. We call it a two-sided test or a two-sided hypothesis. Whereas here, I'm only concerned with one extreme, either extremely less than or extremely more than. And so how that's going to be reflected is in the tails of your distribution. So we already established that we can use a normal distribution with these conditions being checked, right? And so these conditions have been checked, and we can assume that it follows a normal distribution. So our normal distribution here, and I'm just going to draw one for each of these scenarios. Okay. It's going to be centered on P naught because we assume that, that the null hypothesis is true, right? So both of these, it's going to be centered on P naught, centered on P naught. Okay. Then my sample proportion is going to either give me evidence for or against this hypothesis, right? And so my observed P hat might fall somewhere out here, right? And in the in the change option, oh, I forgot I did the, we would replicate it in the opposite tail. Okay. And so this area is what we call our p-value. Oops. Change that. So these give us two-sided p-values, right? And that comes from this two-sided test. Oops. And I'm on a different page here. I don't really want to be quite yet. Okay. This is a two-sided test. Okay. Which equals a two-sided p-value. It's there's a lot of p's, right? But this p-value is actually the probability, so the area and the tails. Okay. Whereas if you are trying to show that the sample proportion is significantly less than p naught, then of course your sample proportion should probably end up down here. And then this is your p-value, is the area and the tail. There. Whereas if you're trying to show that there's been a significant increase, then your sample proportion should probably be higher than p naught. Otherwise, it's hard to use. So if I tell you I found a sample proportion of 0.3, and I'm going to try to use that to show that it's significantly higher than 0.5, that doesn't make sense, right? And so of course the sample proportion has to be higher than your hypothesized proportion. So then this is the p-value, right? Going back to the definition of the p-value is the probability of something as extreme or more extreme. And the as extreme or more extreme, that's what makes it the area and the tails. Okay, and so a probability is the area under the curve, and then as extreme or more extreme is the area and the tails, and which area depends on your alternative hypothesis. So this is a one-sided test. So usually what I'll do is I'll jot down beside my alternative hypothesis, I'll remind myself whether it's a two-sided test or one of these one-sided tests. And we don't specify which side, it's just one side. Okay, so the one-sided test, which means a one-sided p-value. And maybe I'll just use the same description for both of these. We don't need that until the third step, right? So it's kind of hard to make that connection between step one, where we state our hypotheses, and then referring to that in step three when we find our p-value. Okay. So let's see here. All right, so that's step one, is to state our null and alternative hypotheses. And it comes from the question, and it's very hard to do in the beginning, but once you've practiced enough, then you're gonna start to see the patterns, right, in the questions. Step two is to do the test. Now, for the p-value approach, right, we have decided, okay, I'm going to use my hypothesized proportion as my mean, and also use that to find the standard error. And I'm going to use that to calculate a Z-score, right? I'm trying to find the area under the curve, which is the p-value. And so Z is p hat, minus p naught over the standard error, which is now p naught times 1 minus p naught over n. Okay, and I'm going to grab it from the formula sheet, which I put somewhere around here. Just to show you that it's on here. Not that this is the be all end all. You get to make your own formula sheet, right? But here it is on here. So a hypothesis test for P, well, the default setup is this, right? You need to use your question to figure out what P naught is, the value for P naught. But then here's your Z-score calculation, right? P hat, how far is it from my hypothesized P? right? Taking into account the standard error, right? Notice the difference between the standard errors in the Z-score and the confidence interval. And we'll talk about the sample size in the next section, so we'll hold off on that. Okay, so doing the test, right? We calculate how far is p hat, so our sample proportion, from the hypothesized proportion, right? So here, how far is the sample proportion from the hypothesized proportion. Right, that's basically what that calculation is doing. And far, the distance is relative to the standard error, right? If I have a small spread, then a small difference might be relatively large. Okay. So then, step 3, I've called it gather evidence because that's kind of what we're doing in terms of the confidence interval and also finding the p-value. But now that we're using the p-value approach, I would just say find the p-value. So gather evidence or find the p-value. It's kind of more telling. Remember, in the confidence interval approach, this is where we drew that number line just to kind of help guide our way through to the conclusion, right? But now it's actually going to be finding the p-value. And so we can use our Z-score, right? Remember the Z table to find the area under the curve that we want, right? And so we use the Z table or the Z-score from step 2 and the Z table to find the appropriate area under the curve. Area under the curve, which is the p-value. So we know how to, if we have a Z-score, then I can find areas under the curve using the Z table. It's been a while, right? But we know how to do that. And I've got an example that we'll use. And so here, right, this is where I'm going to copy just all of this here, copy. So from the null and alternative hypotheses, depending on what the alternative hypothesis was, that's going to tell you which area in the tail you're going to find, right? And so if you want to show that P is greater than P naught, then you're going to find the area in the upper tail, in the lower tail. If you want to know if there's a change, so not equal to, you're only going to find the area in one of the tails and then multiply it by 2. So in this case, find the area in one of the tails, which is a one-sided p-value, and multiply by 2. Right, you're just going to replicate it in the other tail, and maybe I'll follow that up here to replicate the area in the other tail. Your sample is only going to be in one of the tails, right? But if you want to do a two-sided test, then you kind of pretend that something as extreme or more extreme happened in the other tail as well. Okay. In general, we should be using two-sided tests, right? So we should be using not equal to. It's also really important that you set up your hypotheses that you want to test before collecting data. Now, of course, that's hard to pick up on in our questions because we always say, oh, test this hypothesis. Well, it's not that obvious, but here's some theory that we have, and here is the sample that we collected, right? But in real life, you would set up your hypotheses before conducting any, collecting any samples, right? So in real life, we need to set up our hypotheses. Oops, set up our hypotheses before collecting any data to avoid what we call data snooping, where we say, oh, well, this might be significant. And by significant, I mean rejecting H naught in favor of HA. That's what we call a statistically significant result. Okay, and so, oh, this might be significant because it's so large, and I'm going to go test that, right? But that's not how it's supposed to go, right? We set up our hypotheses. So I have this idea, and then I gather evidence, and I see if it's for or against my hypothesis. Before collecting any data to avoid data snooping, kind of a cute term. And just kind of as a side note, significant is a statistically significant results, which is the same as having enough evidence to reject H naught. So a statistically significant result, which is when we have enough evidence to reject H naught. And I should say in favor of HA. Right. So I realized I'm throwing this term significant around, but it's we're very particular about what it means, right? So significant means a statistically significant result. And how do we get it? Well, that's when we have enough evidence to reject H naught in favor of HA. Okay, so now our conclusion. We haven't actually found a p-value. I've got that example that I want to run through. But once we have our p-value, what we said was, okay, if the probability of seeing something as extreme or more extreme than what we saw, assuming the null hypothesis is true, if that's really small, then that's enough evidence to reject H naught. Okay, so in general, for step 4, which is the conclusion, I'll do a little preamble here. So if the p-value is small enough, okay, and we're going to have a threshold. Well, how small is small? I don't know how small is small, right? But if the p-value is small enough, we have enough evidence to reject H naught. We have enough evidence to reject H naught. We use a significance level or an alpha level as a threshold for what we consider small enough. So we use a significance level or an alpha level is what we call it, but sometimes it'll say significance level, and that is the alpha level. So we use a significance level or the alpha level to determine, or maybe I should say as a threshold, for determining if a p-value is small enough. If a p-value is small enough. Okay. The default alpha level is going to be 0.05. The default alpha level is 0.05, and maybe I'll say alpha equal to 0.05. And this is alpha. But that's a pretty common Greek letter, so hopefully that's okay. Okay, so if the p-value is, and sometimes we'll use a different alpha level. Okay, so 0.1, 0.01, but the default, if it doesn't say, then you're going to use 0.05. Okay, and to link this back to our decision errors, well, the alpha level is our type 1 error rate, right? And so there's always a chance that we're going to be rejecting H0, but we shouldn't have, right? And so, and we're saying, okay, well, if the p-value is small enough, right? So if it's past this threshold, then I'm going to reject H0, right? But there's still that 5% chance or that 0.05 chance that I'm wrong, right? And so this is the type 1 error rate. The alpha level is the type 1 error rate. If the consequences of making a type 1 error are large, right, financially, or even, you know, in terms of health or something like that, right, as a society, if the consequences are large, then you're going to decrease that alpha level, right? You're going to decrease it to 0.01 or something even smaller potentially. Right. If you're kind of, you know, open to being wrong, right, and saying, oh, there is a significant difference when there isn't, then you would increase the alpha level maybe to 0.1. Okay. And so if the consequences of making a type 1 error are large, we would consider decreasing the alpha level. We would consider decreasing the alpha level, right? And vice versa. Okay. So what we've decided is that, okay, if the p-value is small enough, then we have enough evidence to reject H0. Right? So now our conclusion in terms of H0 is either we have enough evidence to reject H0 or we don't. So either the p-value is small enough or it's not. Okay? And so our general blurb here is that, so step 1 of our conclusion is that if the p-value is less than the alpha level, and usually it's given in the beginning of or at the end of a problem in our case. So if the p-value is less than the alpha level, we have enough evidence to reject H0. Okay. So if it's less than the alpha level, we have enough evidence to reject H naught. And then what does that mean in terms of the question? Right? Whereas if the p-value is not less than the alpha level, right, then we do not have enough evidence to reject H naught. So if the p-value is not less than the alpha level, we do not have enough evidence to reject H naught, right? Those are only two options. Nice. And I'm trying to remember where my funny is for this one. Let me see if I can find it relatively quickly. I cannot. Dang. Okay. I'll bring it for next time. I'll find it. I do have a funny. Okay, so there's a lot here, right? But we saw a lot of it while we were using the confidence interval approach. So what I want to do is I want to go through this question. It's from the textbook, and I'm just going to use it as an example. Okay, and I chose it because it has a question about the majority, which I always get questions about. Well, what's the majority? It's more than 50%, right? So it's a 50% threshold. So do a majority of US adults believe raising the minimum wage will help the economy, or is there a majority who do not believe this? Kind of a weird start of the question, but okay. A Rasmussen Reports survey of 1,000 US adults found that 42% believe it will help the economy. And then there's some footnote about just the source, I guess. Conduct an appropriate hypothesis test to help answer the research question. Okay. So first thing we're going to do is we're going to check the conditions, right? And so step 0 is the conditions or the assumptions. We're going to use a p-value approach here. So, so let's see here. I'm only going to check the p-value. Well, actually, we can check for both, right? Why not? First thing we need to check is the independence condition. It doesn't say whether the sample was randomly selected, right? And so here we assume that the sample was randomly selected. We assume the sample was randomly selected. I'm also going to throw in the 10% condition. So 1,000 US adults, is that less than 10% of all US adults? Yes, it is, right? So N equal to 1,000 US adults is less than 10% of all US adults. Right, that's the 10% condition. That one's optional, but I want you to see it just so it's not so scary. Now, the success failure condition. For the p-value approach, hypothesis testing with p-values, we're going to check that n times p naught, which means we need to find p naught, okay, has to be greater than or equal to 10. So what's my hypothesized proportion? So this is where it gets a little bit dicey because I actually have to set up my null and alternative hypotheses before I can go ahead and check these conditions. So it's a little bit intertwined, but the value that I want to compare my my sample proportion to is what? Well, I want to know if there's a majority, right? And so here, let's highlight what I have. So 42% is my p hat is 0.42. My n is 1,000. And a majority is my hypothesized proportion, right? What's the majority? The majority is P naught is equal to 0.5, right? If it's more than 0.5, you have a majority, or on the other side, right, if it's less than 0.5. And the way this question is worded, it makes me think that it's a two-sided hypothesis test because they're asking, do a majority of US adults believe raising the minimum wage will help the economy? Or is there a majority who do not believe this, right? And so I'm kind of a little bit on the fence here for what the alternative hypothesis is, but we'll park and let that for just another moment. So n times p naught is 1,000 times 0.5, which is of course 500, whoops, which is greater than or equal to 10. So that checks out. And n times q naught is also 1,000 times 0.5, which is also 500, which is also greater than or equal to 10. So that also checks out. The optional check is the hypothesis testing, or maybe we'll just say it the confidence interval check, but just for practice, right? Because we haven't practiced a ton. What's the difference? It's going to be n times p hat, which is 1,000 times 0.42, which is 420, which is still greater than 10, and n times q hat, which is 1,000 times 0.68, I want to say. 1 minus 0.42. Oh, in the tens more. 0.58, sorry. Oops, math. 580 is more than 10. Right, so we have the observed number of successes and failures, and we have the expected number of successes and failures, assuming H naught is true. Right, so here, this is the expected number of successes and failures, assuming H naught is true. H naught, that P is equal to P naught, which is equal to 0.5, is true, right? Whereas this is the observed number of successes and failures. So just slight difference. Okay, so we've checked all the conditions. So now I can go ahead and I can assume it follows a normal distribution, and I can find Z scores, and I can use the Z table to find areas under the curve. So therefore, usually we say therefore the conditions for inference are satisfied. Inference encompasses both confidence intervals and hypothesis testing. So therefore, the conditions for inference are satisfied. So then I'm on to step 1, which is to state the hypotheses. I guess I didn't really spend any time talking about what type of question it is, but that's something that you would start off looking at, right? And determining, okay, I've got one sample of US adults, I'm given a proportion. So it looks like it's going to be a one sample proportion type of question, right? And then from there, you would have your H naught is that P is equal to P naught, but I'm going to fill in what that value is from the question, and P is, and I'm still kind of on the fence whether it's not equal to or potentially it's less than 0.5, but because I'm unsure, I'm going to use not equal to, right? Since it is unclear to me which inequality to use from the question, I will use the default not equal to. And then we had, maybe I'll screen, a majority is more than 50%. But because they said, oh, do more than 50% or less than 50% agree with a statement or disagree with a statement. So they kind of covered both. And so that's what makes me think that it's a not equal to, which makes it what? A two-sided test. Okay, and so here, this means that we have a two-sided test, which in step 3, I'm going to use that to figure out what my two-sided p-value is. So now in step 2, I do the test, which with the p-value approach, I'm going to say Z is equal to p hat minus P naught over the square root of P naught Q naught over N. So my Z is, my P hat was 0.42, I want to say. 0.42 minus my hypothesized proportion, which is, I'll put a 0 on there just to match, 0.50 divided by the square root of 0.50 times 0.50 divided by 1,000. I'm going to deal with the standard error, so the square root first. So 0.5 times 0.5 is 0.25 divided by 1,000. And then the square root of that, I get Z is, I found the denominator first, so I'm going to jot that down, 0.01581138883, and then maybe I should store that. 0.42 minus 0.5 is negative 0.08. Once I divide it by that number, and make sure you keep all your decimal places, recall that guy, I get a Z of negative 5.059644,256. I know that my Z table only goes to 2 decimal places for Z. So Z is roughly negative 5.06. 2 decimal places to match the Z table. I also know that negative 5 doesn't show up there, but I'll see that in a second. So then step 3 is find the p-value Here I'm going to remind myself of the null hypothesis and the alternative hypothesis. So H naught is that P is equal to 0.5. And my alternative hypothesis is that P is not equal to 0.5. What that's going to look like is, okay, so here I'm centered on P naught is equal to 0.5. And I found that 0.42 is 5 standard errors below 0.5. So it's really far away from 0.5. So here I have P hat equal to 0.42. But because I want to have the not equal to, I'm going to replicate this area. So I'm going to find this area here. This is the one-sided p-value. And what I want is I want to replicate that one-sided p-value over here on the other side. It didn't happen there, but I'm going to pretend for that two-sided p-value. So now the Z table only goes between negative 3.49 and positive 3.49, right? And so we could use the Z table, but we know that it's is beyond negative 3.49. So here, using the Z table, we find Z equal to negative 5.06 is less than the smallest Z value of Z equal to negative 3.49. So we know that the area in the tail of negative 5.06, all we know is that it's less than 0.0002 or approximately 0. Therefore, we know the area in the tail is approximately 0. I'll clarify here, less than 0.0002. Okay. Even when we replicate that in the other tail, if I take something less than 0.0002 and I multiply it by 2, well, it's going to be less than 0.0004, which is still approximately 0. Right? So we multiply by 2, we multiply this area by 2, and it is still approximately 0, right? Really small. You can never say 0 because the tails never close, right? So therefore the two-sided p-value is approximately 0. Okay. Or less than 0.0004, right? 0.0002 times 2 is 0.0004. Wait. That's really small, right? That means the probability of seeing a sample proportion of 0.42, assuming the true population proportion is 0.5, is less than 0.00004. That's evidence against that population proportion being 0.5, right? And so that's what we're going to take into our conclusion. So our step 4 is our conclusion. And it always has the same format. So I always start with since the p-value. So I always we want to compare the p-value to the alpha level, right? So in this case, it's smaller than the alpha level. We weren't given an alpha level, so I'm going to use the default of 0.05. So here's what I'm going to say. So since the two-sided p-value, since this two-sided p-value is approximately 0, or less than, I'll put in brackets, or less than 0.0004, it is less than our assumed alpha level of 0.05. It is less than our assumed alpha level of 0.05. Right? We weren't given an alpha level. Usually it would end with use a significance level of 0.1 or something like that. And it does not, right? It would be here at the end usually. So I'll follow it up with, it kind of becomes a run-on sentence, but which means we have enough evidence to reject H naught in favor of HA. And then of course, what does that mean in terms of the question? And so here, let's see here. There's no real question that we could reword as an answer, so we need to put a little bit more work into it. So conduct an appropriate hypothesis test to help answer the research question. Well, the research question is, do a majority of US adults believe raising the minimum wage will help the economy, or is there a majority who do not believe this, right? And so we have found, right, that there is not a majority who believe raising the minimum wage will help the economy or don't. That's weird. I don't like that wording. Anyways, I'm going to steal this wording and try to write something that makes sense, but I also only have a minute left, so it might not work out. This means how can I write this? It's such a weird question. A majority of US adults, I'm just gonna steal it. This means a majority of US adults it doesn't make sense. Weird wording. I'll find one that's better for next day. Okay, but I am all out of time, so I don't know. I'll just leave it there. That's a weird question. Well, the wording is weird. So the question itself is fine. Okay, let me know if you have any questions. I'm going to stop this recording, and you guys have your quiz on that opens on Friday.
We have the whole weekend again, right, though?
Yeah.
Okay.
Totally. And this, it'll be up to and including this point. So I'll post a tiny, tiny assignment to practice this stuff.
Okay.
Cool.
Thank
Awesome.
you. Have a good weekend.
You too. See ya.
Bye.